Dr. B. Babu Manoharan, Managing Director, Mrs. S. Jesipriya, Director, Mr. B. Sasishekhar, Principal, Dr. Vaddi Seshagiri Rao, and Dean Research, Dr. B. Parvatavadini, on their absentia. I extend a very warm welcome to our resource person, Mr. Samuel Jigme Harrison, Senior Digital IC Design Engineer, StMicroelectronics, Asia Pacific Private Limited, Singapore. At this moment, I am very proud to say that the resource person is our department distinguished alumni. Last but not the least, I extend a very warm welcome to all participants of this online short-term course on VLSI physical design using Cadence Innovus tool. Let me give you a brief about St. Joseph's College of Engineering. St. Joseph's College of Engineering was started in the year 1994 with an aim of imparting quality technical education to the aspiring youth of India with its state-of-the-art infrastructure and other facilities. Right from the inception, our college aims at offering value-added education suitable for meeting the industrial requirements in India and abroad. Our college is approved by AICTE New Delhi and affiliated to Anna University, Chennai. Under the guidance of our Honorable Chairman, Dr. B. Babu Manoharan, our institution has reached a milestone of 26 successful years. Our college has been accredited by National Accreditation and Assessment Council and has got A+ grade with the highest score of 3.46 out of 5. Our college has been continuously participating in National Institutional Ranking Framework (NIRF) approved by the Ministry of Human Resource Development, Government of India, and we have secured the 160th position in engineering stream in NIRF 2020. The Department of ECE has been existing since the inception of our college and has entered onto its 26th year in its journey of sharing and spreading knowledge. It has been accredited by National Board of Accreditation since 2003. Our department is also recognized as a research center by Anna University, Chennai, and offers part-time and full-time PhD programs. VLSI circuits are used universally in real-world applications. These include microprocessors in a personal computer or workstation, chips in a digital camera, chips in a cell phone, and embedded processors in an automobile. The physical design is the process of transforming a circuit description into the physical layout, which describes the position of cells and routes for the interconnections between them. This short-term course aims in providing a good opportunity to the faculty members, research scholars, students, and the VLSI aspirants to have an insight of the main steps in the ASIC physical design flow. I hope that this short-term course is going to be an informative and a fruitful one. I once again welcome our resource person, Mr. Samuel Jigme Harrison, and all the participants of this online short-term course. Now, I invite Dr. A. Swarnalatha, Professor, Department of Electronics and Communication Engineering, St. Joseph's College of Engineering, to give an overview of this program. Thank you.
Good evening to one and all. By the grace and guidance of the Almighty, we, the organizing team, invite each one of the participants for the first session of our STC on physical design. At the outset, I extend a very warm welcome for all those who are present now for the inaugural session and the first session of our STC. I would like to stress at this point the importance of this topic. Broadly, a complete VLSI design can be segmented into three parts: the front end, the back end, and the testing. Front end deals with the RTL design and verification using a good HTL tool like Verilog or VHTL. And back end starts with the functional simulation, synthesis, chip floor planning, placement, routing, analysis for spec verification. The third segment, which is testing, consists of automatic test pattern generation, back annotation, design for testability, and so on. Each of these segments and their subdomains are huge and have their own advantages. And there is a wide job market for each of these segments in the semiconductor industry. This course presents the workflow of the physical design, that is the back-end design. And the standard industry tool for this job is only two. One is the Synopsys Metagraphics and the leader, which is the Cadence Innovus tool. In this short-term course, this tool is now being introduced to our participants. This is now introduced in most of the university curriculums. And so initial initiation into this tool is already given to the students of every electronics in every university. So the students will have a basic introduction, and this backend is now rapidly increasing because of the scaling in the integration, which is happening very fast nowadays. This scaling of IC chips and the scale of integration, which is increasing day by day, has been a boost to the backend industry. So it is with a very great enthusiasm and pleasure that I present Mr. Samuel Jigme, our alumni of our college, who has been in this industry for the past 10 years. A casual talk between the two of us, myself and my student Jigme, has culminated into this STC over the last 2 months. We are very thankful to Mr. Jigme for having agreed to share his industry expertise to each of us so willingly. It's with a lot of inputs and hard work that he has agreed to do this course, as it is his first of this kind for him. This kind of a course conduction as a course instructor is new to him. So he is doing it for the first time. So we wish him all the best for all the efforts that he has taken so far. We are thankful to Mr. Samuel Jigme for consenting to conduct this course and share his expertise with each of us. We are very thankful to Jigme, and we hope all the participants will enjoy knowing about this backend tool. So his 10 years of experience is what is going to be shared to us throughout these 5 days of the course. So as I said, backend, we are going to see about floor planning, placement, routing, and then checking whether the spec has been verified. So this is the agenda for the 5-week course that we have planned. And in this short duration, whatever is the information that we can share, we would like to share it to the participants. We welcome each of the participants for this short-term course. And now I take pleasure in introducing my team, Ms. Jasmine Mystica. She's the assistant professor in the Department of ECE. Our HOD ma'am who gave the welcome address is Dr. B. Victoria Jansi. She heads the team of Electronics and Communication Engineering in in St. Joseph's College of Engineering.
Hello.
Then we have Mrs. E. Malarvali. She's an assistant professor, again in the Department of ECE. Then on the team, we have Mr. Prabhu. He's also an assistant professor from the Department of ECE. So we as a team pray to the Almighty that with his blessings and guidance that we take this course in the best possible way to the satisfaction of everyone involved. At this juncture, I also wish to thank each member of our college management and the heads of the department, and every colleague for having given us the support and various inputs at every point of time in the organization of this short-term course. I now hand over the session to Mrs. E. Malarvili to read out and introduce the speaker for our session. Over to Malar.
Yes, yes, ma'am. Good evening to all. I am happy to present the profile of our speaker, Mr. Samuel Jigme Harrison. He started his Bachelor of Engineering from St. Joseph's College of Engineering, Chennai. He did his bachelor's degree in the field of electronics and communication engineering between 2004 and 2008. During this period, he was highly involved in organizing departmental activities. He then completed his master's in science, MS, uh, specializing on integrated circuit design, a joint degree from Nanyang Technological University, Singapore, and Technical University of Munich in 2010. He also holds a master's in business administration from Anglia Ruskin University, UK. During his studies in these three institutions, Samuel published journals and papers in different conferences and national symposiums. Samuel Jigme Harrison started his career with Avago Technologies, Singapore in 2010 as an entry level IC engineer. Then he was promoted as the senior ASIC design engineer in 2014, and the company was renamed as um, Broadcom Limited Singapore in 2016. Samuel is currently working in StMicroelectronics Asia Pacific Private Limited Singapore since 2017 as the senior digital IC design engineer. He has 10 years of experience in IC design, specializing in physical design implementation with 90 nanometer, 65 nanometer, 40 nanometer, 16 nanometer, and 7 nanometer technologies. The covering areas like floor planning, place and route, clock tree synthesis, static timing analysis, and physical verification. He received a technical merit award, that is best paper award, in SNUG Penang 2018, conducted by Synapses for presenting a paper titled A Novel Approval in Security Implementation and Clock Tree Synthesis using ICC2. He has also published an article titled Importance of Security in IC Design by the Singapore Semiconductor Industry Association in their technical magazine Singapore Semiconductor Voice in May 2019. Samuel holds membership with various technical societies, to name a few. He is a member in VLSI Society of India, Semiconductor Society of India, the Institute of Electronics, Information and Communication Engineers, Japan, the Institute of Engineers, Singapore Associate, AIES. He is a member in Engineering New Zealand. He is a member in Society of Electrical Engineering, Hong Kong, and he is a fellow member in Indian Society for Very Large Scale Integration Education, Ranchi. He is an IEEE member in Internet of Things Community, IEEE Computer Society Technical Committee on VLSI, IEEE Solid State Circuits Society, Circuits Society. On behalf of the organizing team, now I invite our speaker, Mr. Samuel Jigme Harrison, to take over and start the session. Thank you.
Thank you, ma'am, for the brief introduction. Good evening, everyone, and I'm so happy to be amidst you, speaking to you from Singapore, and very happy to be back in St. Joseph's after a very long time as a resource person. And I especially thank the chairman of the institution, Dr. Babu Manoharan sir, and also Jansi ma'am, the HOD, and also Swarnalada ma'am, who has been coordinating with me for the past 1 month, and also all the organizers and staffs of the Department of ECE. And also welcome all the participants from different parts of India, and I hope that this session will be useful for you as you progress in your studies and also in your workplace. Okay, yeah, so maybe we'll start with the session now. Okay, I work as a senior digital IC design engineer with StMicroelectronics Asia Pacific Private Limited, Singapore. Okay, so now about me, it's just a short introduction. I did my bachelor's in electronics and communication engineering from St. Joseph's College of Engineering in 2004 to 2008, and then I did my master's in integrated circuit design, which is a joint degree program offered by Nanyang Technological University, Singapore, and Technical University of Munich in Germany. This was between 2008 and 2010. And I also did my master's in business administration from Anglia Ruskin University. This was a part-time program from 2011 to 2012. And I started my career with Avago Technologies in 2010, and later it was renamed as Broadcom Limited in 2016. So I started my career as an entry-level IC design engineer, and eventually I was promoted as senior ASIC design engineer in 2014. I'm currently working with StMicroelectronics Asia Pacific Private Limited since 2017. And during my tenure with ST, I received a Technical Merit Award in SNUG Penang 2018 in Malaysia. So this was conducted by Synopsys for their tool users. And the title of my paper was A Novel Approach in Security Implementation and CTS using ICC2. And I also had an opportunity to publish an article titled Importance of Security in IC Design in Singapore Semiconductor Industry Association's technical magazine, Singapore Semiconductor Voice, in May 2019. And as you all know, like, I hold a membership with many technical societies, and I regularly follow up with their updates on latest trends and activities. Okay, so now how is the semiconductor industry in Singapore? The first semiconductor organization in Singapore started in 1968, and Singapore houses more than 60 semiconductor companies, which employs around 35,000 people. So the 60 companies includes design centers, front end, back end, and also manufacturing houses. This industry in Singapore is a very prominent industry, and the government pumps in lots of funds in millions of dollars to promote semiconductor business in Singapore, and this semiconductor industry contributes to around 7% of the country's economy. So we in Singapore we have like Singapore business companies and also companies from different parts of the world. So since government is taking more care of this sector, many multinational companies, they have their Asia Pacific headquarters in Singapore. So my company, StMicroelectronics, also has its Asia Pacific headquarters in Singapore. The technical universities in Singapore, like Nanyang Technological University and the National University of Singapore, they also offer highly specialized programs in IC design and microelectronics to nurture the professionals for the growth of the industry. These courses are offered for both Singapore citizens and also nationalities from different parts of the world. Some information about my workplace. StMicroelectronics is Europe's largest semiconductor chip maker and one of the world's largest semiconductor companies with its corporate headquarters at Geneva. StMicroelectronics also has a very big design center in Noida, and every year lots of internships and massive hiring takes place, because in Southeast Asia, India's Noida design center is a very big design center for StMicroelectronics. StMicroelectronics serves more than 100,000 customers around the globe with 11 manufacturing sites. Majority of the business and design centers are in France, and we have around 46,000 employees worldwide with 18,000 active patents. As I have already mentioned, Singapore is headquarters for the Asia Pacific region, and we have two design centers and 3 big manufacturing sites. So ST has been in Singapore for the past 50 years. We recently celebrated our 50 years in Singapore. Okay, what does StMicroelectronics do in a nutshell? Okay, we build products that enable smart mobility. Smart mobility in the sense we have shifted from traditional cars to digital electric vehicles in high volumes. And also smart mobility results in reducing pollution and congestion. And ST's car electrification ICs, they support a lot for electric vehicles. This smart mobility concept also provides safety for the drivers. And the second important product is power and energy management. So in power and energy management is required for all the devices, and also environmental aspects are taken into account, like green technologies with silicon carbide and gallium nitride. All these contribute to saving energy. So ST has a very big part in developing ICs for power and energy. And the third one is IoT and 5G. As we all know, IoT is the world now, Internet of Things. So it transforms our lives, where we work, where we live, and objects we use with cloud connectivity. So, and ST is also in the forefront of data security with latest cryptographic measures. I actually work in the secure microcontroller division, where we design ICs for smart cards like ATM cards, credit cards, and also secured automobile ICs. And we also design ICs for printer guardrages, and also many secured devices like to name a few is we even work for the British Tobacco, which designs the electronic cigarettes. So in UK, there are lots of fake companies doing this kind of electronic cigarettes. So all our products are the lifespan of ST's products. The design cycle is only around 4 months to 6 months, but we design and develop the very small ICs, but in large volumes, and this contributes to the success of the company. Okay, so now moving on to the 4 important markets of StMicroelectronics. Okay, first is the automotive industry. Okay, the automotive industry is we are leaders in car electrification and car digitalization, and the industrial market is nothing but we are leaders in embedded processing, analog and sensors for the industry, industrial power and energy management. Personal electronics, as we all know, it's smartphone applications, sensors, secure solutions, and power management. ST's many products are also available in Apple's watches, and also Samsung's smartphones. So the fourth one is communications equipment, computers, and peripherals. Here, it's a transformation in communication structure from wire to cellular and satellite. So all the Bluetooth connectivity and everything is now very advanced, and the processing speed is quite fast. So all this ST plays a major role in almost all the leading products now. Okay, so what are the product portfolios of STMicroelectronics? We have dedicated automotive ICs for sensors, receivers, secure vehicles, locking systems, and also to reduce pollution. And power transistors, power conversion ICs, like AC-DC converters, battery management ICs, motor drivers, AC and DC, Bluetooth connectivity solutions, transceivers. And the third one is motion sensors, like accelerometers, temperature sensors, environmental sensors like pressure sensors, humidity identification sensors, optical sensing solutions, light sensors, image sensors, and secure solutions, secure microcontrollers, secure payment solutions, like we have the payment through phones now. So all these comes under secure solutions. Brand protection, the one I mentioned was for cartridges, printer cartridges, because now in the market we have lots of fake cartridges which are sold at a very low price. So the cartridges will have this secure ICs so that it is easier to identify that, between a fake one and a branded one from either Canon or some other brand. And the NFC, which is the near field communication, NFC readers, RFID tags, and the general purpose microcontrollers, which are ultra low power, and digital ASICs, which are the system on chip designs, imaging ASICs for imaging solutions, analog and RF, unique RF analog design technology using BiCMOS, power ASICs, like using silicon carbide and gallium nitride and power MOSFETs. So all these are the main product portfolios of StMicroelectronics, and I'm very happy to share my company's profile with the participants for today. Okay, now moving on to the agenda for this 5 days online short-term course. Today we'll be dealing with the course overview and introduction to physical design. Day 2 will be moving on to Innovus, and we'll be going in depth in floor planning and power planning. And day 3 is for placement and clock tree synthesis. Day 4 is for routing and static timing analysis, and day 5 is for physical verification and basics of power analysis. I'm not sure how many of you are from the industry, or most of the participants are from the universities. So I'm not sure like how much exposure you have for each portion, but during these 5 days, we will try to cover and in depth of each step. Okay, so the course overviews, we will be looking into basics of physical design and Innovus, detailed study of all the steps of physical design, and usage of Innovus in the flow. Okay, so now what is physical design? In the IC design cycle, physical design or backend design is the step which follows circuit design. So we have a front-end team which will design the circuit in a form of VHDL or Verilog. So the physical design team gets the netlist, and then all the circuits are converted into metal layers. So the functionality remains the same, and because this metal layers are only readable in the manufacturing side, so we are converting it into metal layers with all the same functionality, and then all the physical checks are done, and the chip is given to the manufacturing sector. So now this circuit representations are converted to geometric description of shapes with various metal layers, and when manufactured, these metal layers will ensure the functionality of the circuit. So depending on the technology node, the metal layers in each chip will differ. Okay. So this is an in-depth structure of where does physical design lie in the IC design flow. As you see in the figure, we have system specification, which is the team which receives the orders from the customers, and the architectural design, where the architecture is being done for the chip. So the design architecture team works on works on implementing the customer's request, and they look into all aspects of area, power, and the reliability of the chip. And based on the architecture, the functional team they receive the given architecture and they design the circuit in terms of VHDL or Verilog codings. And then from the circuit design team, the netlist is given to the physical design team, and physical design team receives it, and all the important steps of physical design cycle is taking place. And from physical design, it moves into physical verification and sign off, where all the design constraints is checked, and then the output from the physical design team is given to the manufacturing organization, so for fabrication. And then after fabrication, the chip is given to the packaging team, because it has to be covered, and it has to be packaged to resist heat, and also all the weather conditions. And so the packaging is done, and after packaging, the chip is again tested at different temperatures and pressures to make sure that the chip works at different frequencies and different conditions. And then this chip is finally delivered to the customer. So this is the full IC design cycle. And in our program, we will be looking only into physical design and the steps involved. So the inputs of physical design. The inputs of physical design are netlist. Netlist is the input we receive for physical design, and it is from the front-end team in terms of Verilog or VHDL coding. So next is the library information of all the cells in the design. So the library information will have the timing arc information, and it is generally known as .lib. So the .lib will have the timing information for each cell, and we also have the technology file, which will have the pin and other physical informations required for physical design. So now, what are the requirements to be met during physical design? Timing, as we know, in digital circuits, timing is a very important aspect. Timing, as in sense, is setup time and hold time. Timing has to be met, and power consumption should be as low as possible. And also the design constraints are the design should be free from shorts, opens, and there should be no crosstalk noise, and all other physical verification comes into effect. So only when all these conditions are met, the green signal is given for the chip to be released to the foundry. Okay, so what are the significant aspects of physical design? Okay, so the role of physical design significantly increased in the 90s because only in the recent times there has been a scaling of technology nodes, and in the transistor, the distance between the source and the drain, that distance is getting shrinked. So as the distance between the source and the drain, the channel width gets shrinked, we have lots of issues in terms of power, in terms of DRC spacing, and lots of congestion happens. So it is where now more effort and also lots of the tools, tool advancements have been done in order to cater to these kind of challenges we face in today's technology nodes. And also interconnect optimization. So interconnect is nothing but when you connect two cells using a wire, say cell A to cell B using wire. So the lesser the wire length, our chip area will be smaller, and also lesser the wire length, timing will be easily met. So all this optimization. So when we try to lesser the wire length, some other factor gets affected. So the tools like Cadence, which uses Innovus, and Synopsys, which uses ICC2 and ICC, they often keep updating their tools with the latest feedbacks from the customers, so that it is useful for the next generation. So okay, so let's stop with this for now, and we will be having a 2 to 3 minutes short break, and we will continue with the basics and steps in ICT design.
Good evening. As we mentioned in the instructions, we'll have surprise quizzes. So now I am going to post the quiz forms. The quiz forms link will be posted here. Please use this Google form and fill the first quiz. It's just a short quiz of 3 questions. So you can take 2 minutes to fill this quiz and submit it. It's based only on what has been covered so far. So 2 minutes we take for you all to fill the quiz and submit it. Just 3 questions. I request you all to take up the quiz and submit it. Highlight అవుతుంది. సబ్మిట్ చేస్తాను. I hope all of you have completed the quiz and submitted it. This is just to see the attention of the audience is in line with the speaker, because this course is not that easily available. So please let's encourage Samuel by our response. So I hope most of you have got a 3 out of 3 score, and we'll now proceed with Samuel. So I hand over the session to Samuel. Can we start, Samuel?
Yeah, ma'am. Thank you. Okay, so now moving into the second half of the course for today's presentation. First, let's look into the steps of physical design. Okay, so we have 5 steps in physical design. First one is floor planning. Actually, floor planning and power planning come together. So it's floor planning and placement, clock tree synthesis, routing, static timing analysis is being checked in each step, starting from placement till the end, and the last one is physical verification. So this is the basic physical design flow, which is followed in all the industries and also research institute. Okay, so now what is floor planning? Okay, so floor planning is the first and critical step in physical design. It is similar to how we develop a plan to build a house. So we make sure that the house is rooms are well ventilated, and the placing of the rooms is properly planned. Once if the floor planning is not done properly, then it will have other implications for the people who live in the house. So the same applies to physical design. If the floor planning is not done properly, the rest of the steps gets affected. So the role of a floor planner is very critical in a physical design organization. So the floor plan actually helps to define the size of the chip. So and it determines the macro placement. Macro placement is the memories being placed, and also the IO pad placement. IO pads is for power to supply power to the chip. So all this is comes under floor planning, and the main objective of floor planning is to minimize the chip area and the wire length. Why is floor planning helping to minimize the chip area? Okay, once we start floor planning, we will have the basic information of how many memories are present in the chip, and what is the X and Y of the chip, and how are we going to place the chip based on the fly line information, and also which macro talks to which macro. So all this knowledge is required for floor planning, and as we start floor planning and we put up the channels for routing, and we make sure that there is minimum space between macros. So, and the main aim of the floor planner is to make sure that no space is wasted. There should be no empty space and no unused area in the chip. And if we mess up in the placing of macros, then in the later stages it will result in timing violations, and we may have to add more LVT cells to fix timing, or we need to move the macros in the later stage, or we need to increase the size of the chip. Is a big complication. So the basic idea to achieve a good physical design layout is floor planning should be very good. And the second objective of floor planning is to make sure that the wire length is very minimal. So only if the wire length, is the metal layer which connects two macros, if it's as small as possible, then in the later stage we will have less timing impact, and also it will be easier for timing closure and also signal integrity. So all this has to be taken into account when we do floor planning, and we need to make sure that macros which communicate very often should be placed close to each other. So this will will reduce the routing resources. So we won't be wasting many metal layers and long routes can be avoided. So as long as we reduce the long routes in the design, moving forth, we will have less congestion and also good timing closure, because the tools which we use are automated ones, and as we design and place the macros in a very weird manner, the tool will sometimes create lots of jogs in the routing, and it will create congestion. So, and then we have to come back to floor planning. So every time in the second, third, fourth step of the physical design flow, we find some issue, and we have to move some macros, or we have to move some pins. We have to come back to floor planning. So this actually, it will also take up our design cycle time, and so the floor planner has a very important role in the chip development cycle. Okay, so the other designs of physical design, like what I mentioned, is placement, routability, and timing closure. They all depend on a well thought out floor plan. So a bad floor plan will contribute to routing congestion and problems in timing closure. So this will increase in area and also power. So as a physical design engineer, it's a must to take care of floor planning. The second step is power planning. So power planning is a step to be executed along with floor planning, and this creates the power grid network. And the main role is to make sure that power is evenly distributed in the chip. So power grid network, usually it has three types of power strips. One is power strip, one is block ring, and one is power rail. So we will start from block ring. Block rings are the power strips which are drawn around the IPs and macros. So around each macro or IP, there will be a VDD power ring and a ground power ring. So the spacing between the VDD and ground power ring, everything has to be calculated based on the technology used, and also based on the design rules for each corresponding technology. So the second one is the power strip. The power strip is the main power strip which runs throughout the chip, and this power strip it connects the block rings to the main power strip. So this main power strip usually will be in the highest metal layer. So the highest metal layer in the design will be usually thick, and the reason is more current can pass through it, and it has low resistance. So when we use higher metal layers for power, we will have low power consumption and low IR drop when we do power analysis. So as a floor planner and as a physical design engineer, we need to make sure that all the power pins of the macros and IPs used in the chip are properly connected to the main power strip which runs across the chip. So because when they integrate the chip into a board, we need to make sure that everything is properly aligned, so that when they do packaging and testing at the final stage, they have no issues. So because nowadays, to avoid all these confusions with the latest technologies, lots of checks have been put in the tool. Even in Innovus, we have options to check static power and dynamic power, and so we don't have to wait till the end of the flow. We can come back to the floor plan and fix the power strip or increase the width or something. Okay, so the third one is the power rails. The power rail actually it connects the VDD and VSS to the standard cells. So when we do placement of standard cells, we need to make sure that the standard cells are placed in the core rows of the chip, so that the top and bottom portion of the standard cell is connected to VDD and VSS accordingly. So I will explain how to create the rows later when we deal into floor planning. And usually the standard cells have either metal 1 or metal 2 to be connected to power. So in Innovus, there is an option to use to connect this metal 1, metal 2 power using follow pin. So the standard cells have M1 or M2 as follow pin, and it connects to the VDD VSS. M1 and M2 will be the lowest metal layer in the chip. So power planning, it involves the number and width of rings and metal strips, and proper connection of power strips to the power pins. So we need to make sure that all the VDD, all the ground from all the IPs, macros are connected to, or properly connected to the main power which runs through the chip. Once we do the connections, there is verify connectivity in an option in Innovus to check whether VDD and ground is open, or is there any VDD ground shorts with signal nets which will be routed later. So we have standard and checks in each step. So we need to make sure that each step takes care of all these, and we need to fix all the issues then and there, so that we don't face any serious implication at the end, because it's lots of money involved, and millions of dollars is invested for a chip. So one small mistake or one missing power strip and it can lead to a huge loss in an organization. So because if timing is not met, if physical verification is not done properly, and if we have shorts, DRC opens, then the chip is not functional, and after tape out we have to come back again to the design center to do mask ECOs. So that is again it involves lots of money and strain. So the important aspect of power planning is to achieve low IR drop. Okay, so IR drop is like, we all know that V is equal to I into V is equal to IR. So there is a low voltage drop. So IR drop is nothing but it's electric potential difference between two ends of a conducting phase. So we need to make sure that IR drop is low as possible in the chip. Now, moving on to placement. Okay, in placement step, we have placement of standard cells. What is a standard cell? Standard cell is a group of transistor and interconnect structures. So it provides a Boolean logic function. So each standard cell will have lots of interconnects in between. Maybe if the whole chip has metal layers starting from metal 1 to metal 6, standard cells will have pins in metal 2 and metal 3, or metal 3 and metal 4, so that during routing, signal nets are routed only in metal 3 and metal 4. Metal 1 in the standard cell will be for power, metal 3 and metal 4 will be for routing of signal nets. So very small chips will have less numbers, and as we reduce the number of layers for routing, we will end up with more congestion and lots of issues in physical verification. So if we have a good margin of metal layers for routing, it is quite helpful for us for timing closure, and also for good physical verification checks. Okay, so now congestion and timing are the two main constraints taken into consideration. So now in placement step, we have congestion driven placement and timing driven placement. So the tool has all these kind of switches to make sure that more effort is put in by the tool to clear up congestion and timing. So this congestion and timing, as a physical design engineer, we need to make sure that we need to make sure that macro placement is proper, and also the macro placement is based on the data flow diagram, and the pins of the floor plan are properly placed so that the pin talking to an IP is the length is short as possible. So all these contribute to congestion and timing. And also placement of standard cells should be aligned with the power rails drawn in the floor plan step. So we need to make sure that when we place the standard cells, it should be aligned. The VDD VSS should be aligned with the power already drawn in metal 1 or metal 2. Because if the standard cell is flipped, your VDD may short with VSS, so it is a great blunder. So all this we need to make sure we take care of during placement.
Jigme, restart your slides.
Hello?
Yeah, Jigme?
Oh, yeah, actually, my line got cut, and the slides also are not moving.
Okay. So your voice is heard. Daddy, YouTube lo etlunchuku. Okay. We'll give some time for our speaker to join in.
Oh yeah, I think it's fine now.
Yeah. So the responses for the first quiz, we have had around 513 responses. That's a good response. Thank you all. So we have one more quiz which will be shared maybe after a few more minutes. And then at the end, we'll have a feedback form shared, which will have around 10 questions in it based on today's session.
Okay. Okay. So yeah. So I will continue with the session.
Your screen is not shared, Jigme.
Oh, okay.
Share your screen.
Yeah.
Yeah, you're ready now?
Yeah.
Okay, just give me a minute. Yeah. So our speaker is now ready with the slides. He's had a shortcut in the link. We're sorry about it. Now I ask Jigme to resume.
Yeah, okay. So as discussed, placement is very important for the following reasons, which determines the performance of the circuit, the power consumption, the routing ability. Because if there is in placement step, if there is more congestion and if the horizontal and vertical congestion is high, there is no point in moving forward, because as we move forward in clock step, we will be adding more clock buffers and clock inverters, and also in routing we'll be having the signal routes in. So it will keep on it will keep adding more congestion. So it as a physical design engineer, it is our role to make sure that during placement we have minimum horizontal and vertical congestion, and also the density of the chip is minimum between 50 to 60% density is a recommended one. So congestion is usually caused by macro spacing, and during placement, if there is more logic clubbed to one region, so it will cause congestion and overlaps of the standard cells or IPs. So in each step, we have certain checks. We will be looking into it in detail later. So the commands used for each step to make sure that we have a clean design. So to minimize the cell density is what I mentioned now. Recommended cell density is like 50 to 60%, and timing DRCs. Timing DRCs are nothing but max transition and max capacitance. So it is always better to make sure that we clean up everything at the earlier stage. We focus on what are the important requirements in placement step, and we focus and to clear it before we move to the next step, because we in the next step we will be having more other complications. So we may not understand whether the issue is because of the complication at that particular step, or is it because of something else from the previous step. Okay, so the next step is clock tree synthesis. Clock tree synthesis is usually a very important feature in industries, but I'm not sure about universities whether more focus is on clock tree synthesis, because we usually focus on placement, then routing and physical verification. But as VLSI aspirants, like when we target to move into a VLSI industry, clock tree synthesis is very important. So in clock tree synthesis, we make sure that the skew is balanced. Like for example, in this figure shown here, we have a clock. This is at the chip edge of the chip. So this figure actually is CTS. This figure is after clock tree synthesis. So you see here, initially there was only this buffer, clock buffer, and it was connected directly to all the flops. So you imagine like from this point till the end, and from this point till the starting of the flop, there is a difference in the distance of the wire. So when it comes to balancing, it is a very big problem. So and there will be fan outs of nets. So all this will create timing issues. And so to go for a faster timing closure, clock tree synthesis is taken into care in all the industries, so that the clocks are balanced. And if you see here, there is one now actually each group of flops will have buffers and inverters. So all these are clock buffers which are put in, so that the delay is the skew is balanced, so that it will help us in timing closure. So to facilitate this process of clock tree synthesis, clock buffers and clock inverters are used. You may have a question like, why clock inverters and clock buffers? Why are these so special other than the normal buffers and inverters? So this all will be given in detail during our session on clock tree synthesis. So we use CTS to balance the skew and also the delay. And CTS is mainly used for timing closure. And after CTS, the hold violations usually get fixed in the chip. So till placement, the clocks are not propagated. So clocks in the design will be ideal till placement, and only in CTS the clocks are propagated, so that only in CTS we will have hold timing information reports when we run the clock tree synthesis step. And from clock tree synthesis step, we need to make sure that both hold and setup violations are under control. So our main focus will be on both. In placement step, we need to make sure that setup timing is under control, and only then we need to move into clock tree synthesis. So usually clock contributes to around 30% of total power in the chip. So the clock itself contributes to this much power. And if we keep on adding more clock inverters and more buffers, it will consume more power. So to avoid more adding of clock inverters and buffers, we need to have a proper floor plan and proper placement, and the clock tree balancing should be properly done. Okay, so clock inverters help in clock tree building, and clock buffers, it helps in clock tree balancing. As I mentioned, CTS, bad CTS structure will contribute to addition of more CTS buffers and inverters. So it will result in congestion and more power consumption, because CTS buffers and inverters, they actually contribute more power than normal buffers. And during CTS step, if we add like 20,000, 30,000 of clock tree buffers, then we result in congestion, and during routing, everything will shoot up. Okay, so static timing analysis. Okay, maybe we'll finish routing first and then come to static timing analysis. Okay, routing is the process for allocating a set of wires in the routing region. Here, this is the step where all the connections between the macros are done, and all the signal nets are connected. And so this one determines the functionality of the chip, because the first routing we did in floor plan step was only power routes. So that is only for providing power to the chip and also making the necessary power connections. But routing is the process where the signal nets are being routed. So it is the same process using metal shapes. So as I said before, if usually the routing layers will be, they may have 2 or 3 layers for routing, depends on the type of chip and security involved in it. And these metal shapes are interlinked. The change in metal layers are interlinked using vias. So suppose we have metal 2 and we need to switch to metal 3. So via structure is present between metal 2 and metal 3, which makes the connection. So usually in a design, we will have certain metal layers for vertical routing and certain layers for horizontal routing. So because it is not possible to route a full chip if with the same metal layer, so we will have different metal layers for vertical and horizontal routing. But if we work on a standard cell, just on a standard cell alone, standard cell will have few restrictions, so we will have only limited number of routes. But when we come to a full chip design, where we have more number of layers, so that during that process we will have like 2-3 layers for vertical routing and 2-3 layers for horizontal routing. So objective of routing is to make sure that the wire length is very minimal. So when we have a shorter wire length, the timing path will be less, which means that from A to B, which is A is a start point and B is an end point, the wire length is, if the wire length is small, then the timing path will be small, and the number of buffers added in the timing path will be also small, which will lead to good timing closure and also less power. So, and we need to make sure that the number of layer changes is also minimal, and number of vias. So, because each and every metal shape or via structure will add to more area and more congestion. So, we need to plan our floor plan accordingly so that we have proper routing channel between macros and also enough space for routing. So that is why usually the experts always advise us to place the macros, the memories at the boundary, and have more space in the center for standard cell placement, so that we give more room for the routes to play around to ease congestion. Okay, so as a physical design engineer, we need to make sure that the routing channels are well utilized and proper care is taken to avoid congestion. So, but this one is not this one cannot be achieved in one go. Like we may have to go through a few iterations to fix the floor plan, and also during routing we may have so many issues. So this will take few iterations. But once it is once we have a proper idea on how to approach it, it is quite easy. So a good router design will meet timing requirements, and will also have less number of violations in physical verification checks. Like you'll have minimum spacing violations, which will help us in fixing DRCs, and also if there is less congestion in the design, then there are less number of shots. So we have LBS is we have LBS to take care of it. So all this will help us in the physical verification process. Okay, so now moving on to static timing analysis. This is a process to check that the design is free from timing violations. So during static timing analysis, we check for setup time, hold time, and timing DRVs, which are max transition, max capacitance. So this process is very important because we need to know how fast the chip can operate and how fast the input reaches the output, and how well the chip can interact with other devices. So during timing closure, we have a few parameters to see, like between registers, it is called reg to reg timing, and how far the macro is in contact with the IO boundary. So IO timing has to be taken care. So we need to have a proper understanding of timing requirements and timing basics, so that we can place the buffers at the required place, and also we can understand the violation easier. So floor planning, placement, CTS, and routing all contribute to timing violations. So that is why Innovus and ICC2, they have a timing check at each step. So at each step we have timing checks, so that we achieve a good timing at the end of the flow. So the STA tool actually it analyzes the timing paths, as I mentioned, from start point to end point, and it compares it with the constraints of that particular path. So in each physical design flow, we will have a set of timing constraints. So we need to make sure that the timing violations present and also the timing paths observed all meet the constraints. So main goal of STA is to make sure that all the signals clocks propagate well through the circuit, because in the timing path, if a clock is not propagated properly, you will come to know. So all this will help us to make sure that the circuit is working properly. And because in some companies where certain timing paths are not checked properly, this will reflect only when the chip comes from tape out and goes for testing, or even when the customer uses it at his end. So when they trace back, we will come to know that this certain path was not constrained properly, and this has led to timing violations, and the chip cannot function. Either setup will fail, or hold will fail, and we have to go through all the fixes, and it is a big loss for the design center. Okay, so now moving on to physical verification. Okay, this is the final process to ensure that the design is ready for fabrication and all the design rules are met. So during physical verification, we don't check for timing. We check for functionality of the design, and there is a check to make sure that the netlist which we used the netlist which we used initially during the start phase of physical design, the functionality is the same versus the netlist which has gone through all the 5 stages of physical design, and we need to make sure that both the netlist match and there is no difference in the functionality, because the main goal of physical design is to make sure that the circuit is converted into layout and the functionality of the chip should not be affected. And the layout should meet the spacing rules between metals, like it should be clean from shorts and opens, and the minimum width should be met between each metal layers. Okay, now we have physical verification. I have just given the headings of the checks, and we are in our detailed study we will go into each check. So first is design rule check, where is DRCs. It is used for checking spacing violations, min area violations, and there is a proper spacing between each metal layer. And the next one is layout versus schematic check, LVS. It is used to check shorts and opens. As you see in the figure here, there is a short because there is one metal layer of net name clock 20 and another net name clock 10, and both metal both nets are using the same metal layer. So if you see here, there is a short. So this is a very basic example, and when we have a chip with more metal layers, it is even more complex to find the short and fix it. And we have electrical rule checks. Electrical rule checks is to mainly check floating gates and if there is any short between the drain and source. And also we have antenna checks. Then we have latch up checks. XOR check. XOR check is nothing but once the physical design cycle is complete, we will have the GDS. So the GDS is the format which has the metal shapes and also the labels of the nets and also the IPs details. So this is given to the foundry. So we need to make sure that every time we do a DRC fix or LVS fix, we need to make sure that the XOR check between the initial GDS and the final GDS is the same. And we need to make sure that what the check will actually show us the differences in the metal layers. So it is easy for us to identify that okay, our checks have been taken in and we haven't touched any other metal layer. So all this is very important because each metal layer costs a lot to the company. So we need to make sure that every check is done properly. And logic equivalence check is the one I mentioned, that the netlist before physical design and after physical design should match. So any physical design, physical defect in the design will result in non-functionality of the product. So each step in the physical design flow is quite important. Okay, the final step is power analysis. This actually is done using the intermediate checks can be done using Innovus, but the proper power analysis check is done using a tool from ANSYS, which is known as RedDoc. So that is the tool which does sign-off power analysis. But the concept is the same even if you use Innovus or ANSYS. So power analysis, power integrity is the biggest challenge in the industry now because of the shrinking of design in technology nodes. And we have two powers here, static and dynamic power. Static power is the power which is calculated when there is no activity. So for static power, the inputs taken is the current chip without any activity. So because each IP will contribute power, each metal layers, all this will have an effect, clocks will have an effect. So we just want to make sure that without any activity, with just the design, how much is static power. Dynamic power is when the design is active. So for to make the design active, we give a toggling, we make the clocks active, so that to make sure to understand, like at this frequency, if the chip works at this frequency, what is the power generated. And IR voltage drop and electromigration are the two parameters used. So two main parameters we need to take into account to meet power analysis. So this power integrity issues can be usually fixed by either adding additional power strips, or widening the width of the power layers. So all the power integrity issues can be fixed only by modifying the power strips. But we need to understand that for every fix, when we do, we have to go back to floor plan, because power strips can be added only at floor plan step. So it is floor plan is very important, and more time has to be taken to do a proper floor plan, because every time we go back to floor plan, we have to go through the other steps. So this will cost more time in the design cycle. So a good power grid will result in faster power integrity closure. Yeah, so this is the end of today's session. Today's session was just a brief idea of what happens in each step. And from tomorrow, we will be going in depth to basics of each step, and how to approach a floor plan, and what other commands to use, and everything for each step. Yeah. Hope my session was useful for you today, and for all the young budding engineers and researchers. Thank you.
I've just posted the link for the second quiz, and I'll also be posting the feedback link and the final quiz. The feedback link will have 10 questions. Both these forms will now be closed in another 10 minutes. So now for another 3 minutes, we will be closing the second quiz 1.2. And after I post the feedback link in another 15 minutes, we will close down the receiving of responses for that quiz. So now it is time for quiz 1.2, which is already posted in the chat box, and I'm posting it again now. So this is the second quiz for this day. Please take 3 minutes time, fill it up, and post it back. After which, we'll have Jasmine ma'am giving us the instructions for tomorrow's session. After her instructions, we will close this quiz, and I'll post the final quiz. So once we post it, we will be receiving responses for 10 to 15 minutes, and then we will be closing it down. So now I invite Jasmine ma'am to conclude today's session and to give us the instructions for tomorrow's session. And I request Prabhu to close receiving the second quiz in another 2 minutes.
Okay, thank you,
Over
Jigni
to
sir.
Jasmine.
Thank you, Jigni sir. That was truly a great introduction session on VLSI physical design. We believe that our participants, more than 580 participants, they had an eventful, useful, and an enthralling evening. On behalf of the Department of ECE, St. Joseph's College of Engineering, a special thanks to all the participants. Thank you for joining us today and making this day one session a great success. And for tomorrow, I would suggest that please set a reminder for 4:30 p.m. and don't forget to join us here in YouTube Live. The link for tomorrow's session will be informed over mail as well as over our WhatsApp groups. So if you have not subscribed to the WhatsApp groups, please subscribe to one of it to get alerts and reminders about the event. So I repeat, the link for tomorrow's session will be mailed to you, or you can find it in the WhatsApp group. To be there is one more way: you can subscribe to this YouTube channel, because all the 4 days we will be using the same YouTube channel for our live sessions. So you can better subscribe to this YouTube channel, or you will get the link in our WhatsApp groups. Yes, ma'am. That's it.
Yeah.
Okay.
I think, Prabhu sir, we have given time for the quiz 2, and I think we can close it down. Now, the final quiz, which has around 10 questions. This is the quiz which will be used for evaluating, based on which your course certificate, course completion certificate will be issued. So this feedback form has a feedback section and a quiz section. So we request you to take 2 to 3 minutes to fill up this feedback form and to attempt the quiz questions. Around 10 questions are there. So please fill it up and submit it. Maybe now it is 6:03. By 6:15 or 6:20, we will close the reception of the feedback links. So I have posted the final feedback. This is what will be used for evaluating. So 6:15, I think we can, or 6:20. 6:20, we will close receiving the answers for this final quiz. Is that okay? So myself, Swarnalata, from the Department of EC, and my team handling the STC on physical design using Cadence Innovus tool are now signing out for today. So this link, please, we will be online for another 10 minutes so that the chat is available for you to take the feedback form. For another 2-3 minutes, we'll keep the broadcast live. So in that time, please copy the link and start filling it and submit it. Thank you, Jigme, for the wonderful session and the time that you have spared. We hope that this will be an encouragement for you to do further such things, and we hope that tomorrow's will be more interesting and more insightful into the aspects of the tool, and the participants will be able to appreciate what is being shared by you. So wishing each one of you a very nice evening. Thank you. Wishing all of you a very nice evening and fruitful learning. Thank you. I think now we'll ask Mr. Jigme to take up the queries from the audience. Jigme, can you please go through the live chat?
Yeah.
The last few questions alone. I think most of the previous ones are answered. If you find any significant questions in the live chat, you can answer them.
Yeah, actually, there was one question. If there is placement and routing problems, how do we optimize the design? For that, actually, in placement, we have a few switches. Like there are possibilities to group the logics together so that the tool places the standard cells which talks to a particular macro in one location, so that it helps for routing. But if there is an issue in placement, it is better to fix it before going to routing. So if there is usually in placement, we check for horizontal and vertical congestion, and also setup time. So and density. So all these four are the main factors we check in placement. So it is better to fix it in floor plan and then move on to placement. And then when we go to routing, we may face new issues like congestion, and there may be a long net routing. So we need to particularly analyze the timing report and then look into how is it possible to reduce the buffers or hand route it. So we have lots of other possibilities. So it depends on your design and how well is your floor plan. Okay, and there is one question from Pradeep Roy. What will be the approximate size of a design? So the size of the design will be determined using the aspect ratio. So this one we will cover more in detail in tomorrow's session, because I have few slides on how to determine the size of the design. So that will help you to have an idea on it. And will the same designer be responsible for the convergence of all stages of the flow? It depends actually. In my previous company, we were 5 people in a team, so each person will take care of one task. Because even if there is even if a person has to do routing, he should have the knowledge of STA, and he should have the knowledge of placement. So whatever role you are assigned to, you need to know the full design cycle and also basic concepts of physical design. Because if there is a complicated block which has more than 100 macros, if there's a very big chip, and what they do is they partition the chip into few modules. So each designer gets to do a few modules. So in that process, he has to take care of from floor planning till the end of physical verification. So each physical design engineer should know all the five stages of the flow. And majority of the companies these days, they prefer the same designer to take care of everything, because he is well aware of placement, his placement done, and he is well aware of his CTS applied and what are the challenges he faced during CTS. So it depends on the complexity of the project and also the resources available in the team. Yeah, next 4 sessions, it will be in-depth study of each step. What will be the goal of floor planning? What are the inputs for floor planning? What is the expected output? So what has to be taken care of, and what are the switches used to check floor planning steps, and also the basic knowledge of a floor planner. It is how the course is planned for the 5 days. Any open source tool available for physical design? usually we have only Cadence and Synopsys, so it is that is what I know, because even in universities these days they have licenses for Cadence and Synopsys physical design tools. So it is I don't see any open source tool for physical design. Tools used for verification in industries, for physical verification, I guess. Physical verification, we use Caliber, Mentographics. We use Mentographics tools. But even in Innovus, for each step, you can check shorts, you can check opens using the Innovus commands. But for sign-off aspect, we usually have a dedicated tool and a dedicated engineer, because when you consider a full design, it will have more than around 200-300 shots and lots of opens. So we need to analyze the shots and opens. So a dedicated engineer is usually assigned for physical verification, and the tool is the run is separate, and it is different from the physical, the Innovus place and route flow. But the fixes are done using Innovus, and then again the fixes are done at the last step of the routed database, and it goes for again physical check.
Jigme, there's one question. Area
is measured using
area
layout.
is measured in dimension of a design or components like LUT count. Not clear idea about the parameter area in a research paper.
Okay, so usually area, when we take area for consideration, we usually take take into account the routing resources, the channel width, and also the number of macros, the macro size. We determine the macro size, the macro memories, IPs present in the GDS in the design. So all these we take the dimensions, and then we calculate it, and based on the channel spacing, because for each technology node we have certain spacing rules to be met in the design rules. So we need to, so based on that, we can calculate we can use it to calculate the size of the chip, and also the power strips matters. Like the space between the power strips is different. So in a design, in a floor plan, how many power strips has to be put in? Everything has to be taken into account before we design the area. But usually, if it's a standard procedure in a company, we usually they refer to previous projects, and based with the previous projects, it comes by experience. But there are some formulas which can be used directly to have a brief, rough idea of the floor plan, so that we will look into it tomorrow. But everything comes by experience, but you have certain basics to be followed, so that you will have a clear idea on how to proceed for floor planning. Suggestions for gate count. Gate count, actually Cadence, the Innovus tool, the latest Cadence Innovus implementation system, it can handle up to from 5 to 10 million instances in the design. So they keep on improving their versions. So if the gate count is more in the design, then it implies more runtime and also complication in timing closure. So if the gate count is more for design, or if there is a design is very big with lots of instances, then usually the physical design team will plan to partition the chip into few modules, so that the complexity is less when we build modules, and then we integrate it at chip level. So the timing has to be met within the block. DRC, LBS, and all other physical verification steps has to be met within that particular block. And when they integrate at top level, it's only the block to block interaction in terms of timing takes place. And when they integrate the blocks at top level, we have top level DRCs verification has to be done at top level. But timing wise, we will try to fix timing within the block itself, so which is quite easy, because within the block, when we split the design into lesser number of into more modules, then we will have clocks, less number of clocks for at top level. So clock balancing is quite easy, and it is easier for design execution. So it depends on the complexity of the chip, whether there is a need to partition. Because in my previous company, every chip has to be partitioned because it was for processors, CPUs, and everything. But in my current company now, we don't partition the blocks at all. So we just have a floor plan. We put in IPs. We do floor plan placement, clock synthesis, routing, and because the chip size is very small, and the main feature we focus on is security. So timing closure is quite simple. So it depends on the complexity of the design. Specialized area for PhD. Actually, I'm not aware of how physical design has impact on research, but I see lots of IEEE papers coming up on physical design in terms of congestion, timing, and all. So I am not sure about any particular area for PhD. Maybe timing analysis, and right now, since we focus on shrinking technologies, power integrity will be a good option also. Hello?
Yeah, Jigme?
Okay.
Yeah. You want me to read some more questions, or shall we close?
No, I'll read it. Okay, so any open source tool for physical verification? I have no idea, because in industries we usually use Caliber. So I'm not sure about any open source tool. And apart from Innovus, you can also focus on ICC2, because now majority of the companies, they are also switching to ICC2, because ICC2, I heard it helps for these new lower node technologies. So yeah, Synopsys also is quite coming up with new features for implementation, and also power analysis. So apart from Innovus, you can focus on ICC2 and direct research area in this domain. I'm not that particular on how is research being done in this area. Yeah. Power integrity issues will be solved by widening width of metal layer, but it will increase area. Yes, when you increase the width of the metal layer, it will increase area. So with the main target to fix power integrity is, you need to make sure that your floor plan is done properly, your routing channels are proper, and once if you depending on the power strips, the area of the chip is initially designed during floor plan step itself. So if you take into account all the power requirements, all the VDD VSS power strips to be drawn, all the connections to be done, and also some we also have analog nets. Some nets has to be shielded also. So all this has to be taken into account during floor plan. And so in that case, during floor plan itself, there will be a negotiation on area, so that the customer has to agree with this area. So, and there will be floor plan reviews, so that experts will come in to give more ideas on how to stay with a particular area and so on. Okay, for Linux commands like gvim and all, there are in the internet there are a lot of Perl references, short Perl handbooks which are used exclusively for VLSI physical design. So those kind of handouts are quite okay, because you need to have some basic coding knowledge, so that it will be easier for you as you move on. But the Linux commands are like the basic ones which you can find out in Perl references, and also small shortcuts is fine, because it's just only minor work on Linux. But the major work as a physical design engineer is you need to put more focus on Perl codings, because there'll be lots of scriptings required. So if you have good scripting knowledge, then it is a very added value for you in your career. Masters in VLSI, even you can in India there are lots of opportunities in IITs, but I'm not sure how far is the research being done there. But for masters you can try, if it's in closer to India, you can try Taiwan, you can try Japan, you can try Singapore. Singapore has lots of universities which offer masters in IC design. Or you can also try Europe and Germany, because they put more focus on technology in these countries. And last option can be US, because US, even though US has lots of semiconductor companies, there's no particular focus on IC design. Like majority of the universities there have VLSI. But when we see countries close to India, we have specialized universities which offer these kind of programs. Before entering a VLSI firm, you need to know the basics of VLSI, because as a fresher, the expectation from the industry will be you need to have good knowledge of digital logic circuits. So we need to know all the full adders and all the you need to have a good understanding of semiconductor physics, and also digital logic circuits if it's for VLSI digital design. But if it's for analog or RF, then the basics are different. So for VLSI, you need to have good knowledge of digital logic design. So that actually plays a very important role for your interview. And you have lots of interview questions nowadays available online for each company, and you have your resource materials are plenty, not like those times when we had only books to refer. So you can, whenever you're free, you can go through it. Microelectronics, nano electronics also is a quite emerging field now, or than microelectronics. So both are good. Actually, even if you work on nanotechnology, your fabrication has to be done in a fab. So you need to have microelectronics knowledge. And so nanoelectronics, microelectronics, IC design, analog IC design, RF IC design, mixed signal, have more opportunities. If you are good in analog IC design and mixed signal IC design and RF IC design, your market value is different, because digital logic design is easily understandable by everyone, but this is even more specific, and you need to have more knowledge on it. So yeah. You can do your bachelor's, you can, and then in master's, after your master's, you can concentrate on one particular area when you go for a job.
Jignesh, thank you very much for that time that you have taken.
Sure.
And I think you have answered at least 80% of the questions that were asked. So Jigme's email ID and LinkedIn profile is already shared. So any queries, you can also contact him through that. So I think now we can close this session. And thank you, one and all, for being with us. Thank you.